Hi, in this project, we investigate the communicative efficiency of spatial deictic demonstratives in human languages. Spatial deictic demonstratives denote spatial relations between speakers and referents and play a crucial role in cognition and language processing. Examples in English are expressions such as like here and from there. The meanings of these demonstratives can be divided into two separate dimensions. The first one is distal level. It denotes the distance between the speaker and the referent, and it increases as the referent is further apart from the speaker. For example, if the referent is very close to the speaker, we call this distal level D1. In English, the word is here, as in Mary is here. Similarly, if the referent is further apart from the speaker, we will call these distal levels D2, D3, and so on. The second dimension is the orientation, or the relative movement between the speaker and the distal level. If the referent is moving towards the distal level, we call this orientation go, as in Mary is going there in English. Similarly, if the referent is staying at the distal level, we call this orientation place. And if the referent is moving away from the distal level, we call this orientation source. Here are all the spatial deictic demonstratives in English arranged in a 3x3 table. So each row denotes a different distal level, and each column denotes a different orientation. Notice that in English, we use the same word for go and place, and the same word for D2 and D3, since words in the parentheses are optional. For instance, when you say Jamie is going there, what you actually mean is Jamie is going to there, but the preposition to is omitted. On the other hand, in Finnish, as is shown here, each meaning gets its own unique word. There are a total of 21,146 theoretically possible ways to partition the 3x3 meaning space with words. Two of them are the ways adopted by English and Finnish, as we've seen before. There are also these theoretically possible but not attested systems shown in the bottom row. Out of these theoretically possible ways, only 34 of them are attested in 221 languages in a work compiled by Julia Nintemann and colleagues. Their work is really what make our analysis possible. With their data and our model, we now ask the following question: how efficient are the spatial deictic demonstrative systems in real languages compared with other unattested ones? Okay, so what do we mean by efficiency? Let's do a quick overview of the communication model here. The speaker sees a word state U and forms a mental representation M. Then the speaker articulates a word W, depending on the language, and the listener recovers the meaning M prime based on the word. There are two quantities pertaining to efficiency. The first one is informativity, which is how similar the perceived meaning is to the intended meaning. The higher, the better. The second one is complexity, which is how complex the mapping is between the meaning and the word. So in this case, the lower, the better. Ideally, we'd like a system to have the maximum amount of informativity and the minimum amount of complexity. But these two standards cannot be achieved at the same time. For example, consider the two potential systems here. The system on the left has the maximal amount of informativity, since there is no confusion between word and meaning, since each meaning gets its own unique word, but it is also at the same time maximally complex. Meanwhile, the system on the right has the minimal amount of complexity, since there is only one word to express everything. But, well, in this case, it is also minimally informative. So the question is how to balance these two factors to make a communication system most efficient. A free parameter in our model here is how the word state is mapped into the speaker's mental representation. We assume it is dictated by perception and thus independent from languages. We define this mapping function in terms of cost for confusing one orientation with another, specifically the cost for confusing place and source, and henceforth place-source confusion cost, and the cost for confusing place with go, and henceforth place-go confusion cost. And of course, if if the mental representation is accurate according to the world state, there's no cost. So the cost here is 0. So we calculated the informativity and the complexity for all the 21,146 hypothetically possible systems and plotted them on this information plane. The horizontal axis is the complexity, whereas the vertical axis is the informativity. And here goes the result. The blue dots represent the attested spatial deictic demonstrative systems, which are jittered to avoid overlap. And the gray dots are all other hypothetically possible systems. All of these points are bounded by the orange line, which is called the efficient frontier. This line marks the most informativity a system can possibly get, given a complexity. Hence, the region above the orange line is not theoretically achievable. The plot shows that most real systems are very close to the optimal frontier, hence having generally very high efficiency. We also show some example languages in each cluster that are very close to the frontier: English, Irish, German, and Finnish. There are also, of course, languages that are way below the optimal frontier. I can tell you more if you are interested afterwards. So our results add deictic demonstratives to the growing list of lexical semantic domains, whose form can be explained in terms of information-theoretic efficiency, such as color terms and kinship terms. We also found that to make the spatial deictic systems in real languages most efficient, the place source confusion cost needs to be greater than the place goal confusion cost. And this is consistent with previous studies regarding the goal source asymmetry in the Coxide literature. What do the most efficient lexicon look like? On the right, we plot the theoretically possible paradigms that are closest to the optimal frontier at the top, and real paradigms in our database that are closest to the frontier at the bottom. We can see from the graphs that many of the optimal simulated lexicons are not attested in real languages. Specifically, there are like 5 out of 8. So these seem to suggest that there might be some driving forces other than communicative efficiency that shape the spatial deictic systems in real languages. One of them could be systematicity, which is the syncretism of patterns at different distal levels. Specifically, if there is a place goal source pattern at one distal level, it also tends to hold at other distal levels. This can be illustrated by the 2 tables below. On the left is a systematic language, English. But if we replace the word at D2 place, which is the word in the middle, with the word here, it will become less systematic and hence go into this language called fake English that I call, because the orientation pattern at distal levels D1 and D3 no longer holds at distal level D2. We suspect that real lexicons tend to be systematic, in addition to being communicatively efficient. And this is everything. Thank you so much for listening.